Now that we've studied computation graphs, let's reason about the execution time of the computation graph on different numbers of processors. So what we'd like to do is try and understand what possible execution times we could have for a graph on p processors. So T sub p is the parallel time on p processors. So as an example, let's go back to a computation graph you had seen earlier with S1, S2, S3, S4, S5, S6, and give these execution times. So we have 1, 1, 1, 1, 1, and 10. And what we had seen earlier was that the amount of work in this graph adds up to 15, adding up all the times. And the critical path length, the longest path, is from S1 to S6, so that's 11. Now, looking at this definition, what's the execution time of this graph on one processor when p equals 1? Well, that one processor, the total execution time has to be 15, because even though it has a choice as to the order in which it can execute these statements, it has to go through all the statements, and it will take 15 units of time. For two processors, we had earlier seen multiple schedules, one with 11, one with time 13. So if we pick the one with time 11, we could get an execution time of 11 on two processors. On three processors, we cannot do any better than 11. That's the critical path length. So no matter how many processors we have to take at least time equals 11 units, and so on. So what we've seen is we've reached a point of diminishing returns in terms of adding more processors, because we've been limited by the critical path length. So one observation that this leads to is that the execution time on p processors must be at least as large as the critical path length, regardless of the value of p. There's another interesting observation that we can make, is that for p processors, if we take all the work, and the best case would be to divide it up evenly among all the p processors. So the parallel execution time must also be greater than or equal to the ratio of work divided by p. Now, with these upper bounds, we can reason about the best case for the parallel execution time. Another useful definition is one called speed up. So the idea behind speed up is, if you have p processors, how much faster can you go compared to one processor? And it's the ratio of the time taken by one processor divided by the time taken by p processors. So over here, for example, the speed up with two processors was T1 divided by T2 is 15 divided by 11. So it's about 1.4 or so. One observation that follows from these inequalities is that the speed up with p processors must be at most p. So you can think about it analytically or intuitively. Intuitively, you're throwing p processors at a computation graph. You can do no better than going p times faster than the time on one processor. Analytically, if you look at this equation, work is the same as the time required on one processor. So this says that from here we can see that T1 divided by Tp must be less than or equal to p, if you just work this out, and that tells you that the speed up must be less than or equal to p. So there's one interesting observation to make over here. If you have a computation graph where some fraction of the work, let's say q times work, is sequential, and then everything else in the computation graph can be parallel, and this is 1 minus q times the work. What is the best case speed up we can envision over here? Well, one thing we can observe is that the critical path length, because this is sequential, has to be at least q times work, and the best case speed up in this case must be less than equal to 1 over q, because even if you were able to run all the other work in close to 0 time, you would at least take q times work time for the execution time for any number of processors, for as many processors as you want. And so the best case speed up is 1 over q. For example, if q was 0.1, then the best case speed up would be 10x. If only 1% of your program was sequential, q was 0.01, the best case speed up is 100x. This observation dates back more than 50 years. It's due to Jean Amdahl, and so we refer to it as Amdahl's law to say that if a certain fraction of your program is sequential, the best case speed up would be 1 divided that fraction. And what it does is remind you to look at your parallel program and look for these sequential bottlenecks and figure out ways of coming up with new parallel algorithms to address the bottleneck, so that we can address the issue that Amdahl's law warns us about.